Hi everyone. This is the either the fourth or the fifth segment of the mineral chapter, and on the very last segment, I have already started to talk about the physical properties of the minerals, which includes the crystal form, cleavage, the color of the mineral, the luster, the hardness, trick, acid test, magnetism, and the taste. So let's jump into the mineral form. Um, every mineral grows in a specific shape, and it is usually dictated by the inside crystalline structure and the chemical composition. Um, these two actually will make a set of symmetric elements, um, and based on how much symmetric elements the mineral have, they will belong in 6 crystal systems. And of course, inside the systems there are like classes. Really, it's about 42 crystal classes, which you're lucky you don't have to memorize. I had to long time ago. But the most important symmetric elements would be the just the symmetric plane, and then the rotational symmetry, which could be 3, 4, and 6. And so this will bring the different crystal uh, systems. And the only way you can see actually the crystal form if the mineral grows into an empty space. Such, if you think about like in a igneous rocks, you can think of a vog, like a gas bubble, which is going to be empty afterwards, and whatever liquid is in there or it diffuses in from outside, it will, as the water slowly goes away, it will actually precipitate the crystal, uh, based on the composition of the fluid in that hole. Um, so the only way to see the crystal form is if it happens this way. Most of the time, however, every mineral in every igneous rocks will have the crystalline structure, but you have to use X-ray machine to define it. So when you go out and find all those white quartzites along the roads, and like a lot of the fences around Franklin County or Floyd have been built from those quartzites and quartzes, and they do have the inside crystalline form, but they don't show it. So you pick up the mineral, you have to have an X-ray done on it to be able to tell what kind of crystal system they belong to. On this slide, you will see a couple of crystal forms, like that's the aquamarine, beautiful. You can see the 6-sided forms, like right here, it has 6, so it's a hexagonal system. The pyrite cubes, most of the time the pyrite will have this cubic shape, which some people think that it was carved, but no, this is the way it grows. And that's the other very common form of pyrite. Now this is a common form of calcite, the scalenohedra, and this is interesting. That's the naturally occurring diamond's normal shape, the octahedra. The quartz crystallizes in hexagonal systems, so very many times you will see the trapezoid, we call it, or a hexagonal prism, and on top it's the pyramid. And this here is another typical quartz. We call it the Herkimer diamond, but it also shows the typical hexagonal form of the quartz. Okay, the next one is the cleavage. And it's interesting, when I first came to the US, the only way I learned the cleavage is the way the mineral breaks. But then my students were laughing at me and I didn't understand why. But then somebody actually did tell me. So it's kind of an interesting thing that in English, so many words have different meanings. But anyhow, when you break a mineral, like with a hammer, you hit a mineral, it has two choices. Either it will cleave along flat, shiny surfaces, or it will break very irregularly. When it breaks irregularly, we call it fracture. And when it obviously have cleavages, like the way you do it is that you So I'm back. I don't think I can show it to you. This camera is not that good. I mean, the my camera is not good enough to show crystals, but there is one I brought, so I'm gonna show it to you. This here is a beautiful hexagonal crystal system. It's a calcite with a very typical scalenohedra. That's how it looks like. It's very beautiful. I think I can show this, but I don't think I could show the cleavage. Anyhow, the cleavage, when you hold the mineral and you turn it, you have to look at the mineral, turn it, and if the whole side, um, will shine at the same time, even though it has low steps, that still means that the mineral has cleavage. However, when we do have cleavages, it could be absolutely perfect. When it's perfect, it has no steps, nothing. It just very, very, very shiny, and the whole side of the crystal shines at the same time. Um, then it, of course, can be from perfect to imperfect, good, distinct, and indistinct, and poor, just like humans, interestingly. Minerals can have one, two, three, or four ways of cleavage. When you look at the different ways of cleavage, of course, ask me in the lab. I'll help you with it. When you have two parallel sides with cleavage, that counts as one. So one, two, three. So you can have one, two, three, and four ways of cleavage. I have this YouTube video here. If you watch it, actually the guy has a really good camera, so you can actually see the close-up of the cleavage also. So there is a bunch of help out for you. And I actually put it right here, so when you do play this, you actually can see it. And this slide just shows you the conchoidal fracture here, the one way of cleavage, the two ways, like this is one, two, the three waves, that's one, and the parallel side is also that one. Two parallel side, two ways, and the third one is right there. So same here, it's also three, it's one, two, and three. One, two, and three. Remember the one, two, and three. Remember the parallel sides the same way. The next physical property is the color. The color basically, if you think about it, is the first thing you see in a mineral. However, that is probably one of the most misleading property, because the same mineral can have very different colors. Like on the slide right underneath, this is all different diamond colors. These are all naturally occurring, and as you can see, the diamond can be any color. Basically depends on what kind of impurity is in the liquid from which it's growing. I have this slide on which you can see what kind of element causes what kind of color. One interesting one is the uranium, which produces one of the most beautiful yellow color, and they have colored glasses with it before they knew that actually it's radiating. The copper, of course, can produce blue and green. Manganese can produce pink, and so on. So you can read it for yourself or figure out what causes the color of your the stone in your earrings or in your ring. Like I have a pretty emerald right here. No, right here. That's like my emerald right there. I don't know if you see it right there, which is green. The luster is the next one. To me, luster is one of the most subjective mineral property. But there is one thing which you can use it for sure, to separate the metallic and the non-metallic minerals. When the luster is metallic, you know that it's a mineral which has some kind of useful metal in it, and then the non-metallic can be divided into other ones. But I really want you, especially in the lab, decide the luster for yourself, because you're the one who's gonna recognize the mineral, so you have to know the luster for yourself. So if you see a mineral and you feel like, oh, this is glassy, But somebody tells you, no, 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 this is greasy. Don't believe them. You have to know it for yourself. That is one property which you can use to recognize the mineral, but you have to write down, describe the luster for yourself. So that's the luster. The luster is the shininess of the mineral. The next one is the hardness. And the hardness is the mineral resistance to scratching. And we decided relative to the standard hardness scale, which was made by Moose, and you can see it right here. And you don't have to know this scale. I want you to know 1, which is the talc, 7, which is the quartz, and the 10, which is the diamond. So just know the 1, which is talc, the 7, which is quartz, and the 10, which is diamond. You must also understand that not only the talc is a number 1, but talc is the standard of number 1. Like graphite is also 1, kaolinite is also 1, and so on. So make sure that you understand that these are not the only minerals with that hardness, but they are the standards for that hardness. I also wrote down some tools you can use. Like your fingernail is good for 2.5. So if you can scratch the mineral, that means it's less than 2.5. Copper penny is like 3. The glass plate is about 6. And the steel is about 5. The steel nails. So you can use these things to scratch the minerals and decide what kind of hardness does it have. The next one is the streak. For the streak, we use the streak plate, which is a white porcelain plate with the hardness of 6 or 6.5. So you can also use it for hardness definitions. When you try the streak, that means that you rub the mineral on the streak plate, and you're gonna look at the color of the powdered mineral. In a couple of minerals, it's a very, very useful characteristic, as you will see. And I have like 3 really important ones. The pyrite will always have like gray streak. That means that if you have gold, that will have a yellow streak. But at the same time, the pyrite will have dark gray streak. So it's always easy to separate the gold. If you see some yellow metallic mineral and your heart starts racing, oh my God, I found some gold, then just break a little plate or porcelain something and look at the streak, and you will right away know if it's pyrite what you found, because pyrite is fool's gold and it's very, very common. It's easy to find. So a lot of people think if they find something yellow and shiny that they found gold, but in real life it's most likely pyrite. But as I said, you can really separate the gold from the pyrite by using this low streak plate. The next one is the acid test. For the acid test, in class, you will have this low hydrochloric acid bottles. It's not very dangerous because it's only very weak hydrochloric acid we use, but still you don't want to drop it on other people because it can cause like skin irritation. But when you put the hydrochloric acid on calcite, what will happen, like calcite is calcium, Ca, CO, 3, that's a 3, so this is Ca plus HCl, what we put on HCl, and it will go into calcium chloride, so it's Cl2 plus CO2 plus H2O. So what actually you see when you do this test is the water, I mean the CO2, because it's a gas, and it will bubble out. So it's effervesce. Okay, so on the calcite, the CO2 will effervesce. And that's what you see like on this figure right here. You see the effervescent, It's like any kind of gas which comes out will bubble up. So that's what you see basically. Other than that, you can see the hydrochloric acid goes into CO2 and water and calcium chloride. So nothing is dangerous after the reaction have happened. So that's the acid test. And the only mineral which will do that, which will react to the acid, is the calcite. Calcite will very vigorously effervesce. And the other which will do stuff with it is the dolomite, but the dolomite only does it just a little bit because the dolomite has magnesium with the calcite. Dolomite, this is really a T here, right there. So calcite and dolomite. The next thing is the magnetism. When you have a mineral which naturally magnetized, then if you touch it with a magnet, it will stick to it, just like on this picture right here. And the only mineral which does that is actually the magnetite. Netite. Not very good, but it's magnetite. And I wrote it down right here before. So the only mineral which will do that is the magnetite. So if you have a mineral which sticks to the magnet, then you know you're working with magnetite at the time. And this one is the taste. My thing is that please don't just taste any minerals until I tell you so. Don't taste, because there could be some toxic chemicals in minerals, so you do not just want to taste it. So ask me if you should taste anything before you do it. Now we are at the mineral groups. We just finished the physical properties of the minerals, and we are at the mineral groups. There is about 4,000 mineral existing, which is crazy. Can you imagine memorizing it? I had to memorize a whole lot of it, and it's not like an excuse or anything. You will only have to memorize 25 of them. The interesting thing that even today they still discover about 40 new minerals, and these are just local diverse minerals. Most of the time it doesn't really happen very often anymore. Most of the time it's going to be in the labs where they have scanning electron microscope, and these are just microscopic low differentiation of some other minerals, and they name it because people just like to name stuff. But if you do look at the most common minerals, we also call them rock-forming minerals. We don't have that many, because what we realize is that if you look at the Earth crust, there is only 8 elements which are extremely common in there. And this is where I will come back in the next segment, continuing from the 8 elements, okay? Bye for now.